Let us now study about the theory of standing waves. You learned earlier about traveling waves or progressive waves. Now, progressive waves were those waves in which the energy or momentum from a given point moved in all directions or in particular direction, and the energy or momentum will not return to the source. But if we take a case where, for example, like a string like this, where a string is attached between 2 points. Suppose somewhere, imagine at some point we create a disturbance. For example, imagine that at this edge, by some means, we create a disturbance continuously. So at this point, by some mechanism, if we create disturbance continuously, or at any point if we create disturbance, then what happens is there is one wave which will move like this, and this wave, if we produce disturbance at this point continuously, then waves will keep on moving in this direction, and also waves will reflect and come back. So here we have a condition where we have two waves traveling in different directions. When these two waves superimpose, then what we get here is something called as standing waves. In case of standing waves, the energy is confined in the given region only. This is called as standing waves. An example is given here. For example, as shown here, if we have a string and if we produce disturbance at both the ends like this, we get a pattern of this form. There are some points where the displacement is minimum or 0, as seen here. Disturbance is 0 here, it is 0 at this point, it is 0 at this point, it is 0 here as well as here. So these points where disturbance is 0 is called as node, and there are some points where the disturbance is maximum. Example, for this point it has maximum displacement like this, and a point here also has maximum displacement like this or like this. These are called as antinodes, and these regions are called as loops. So here there are 4 loops. Now we'll find out what is the equation for a standing wave, and also at which point we will get nodes as well as antinodes. One more example which is practical could be like a string. So even in, so like a guitar, we have strings where we get standing waves based on where it has been plucked. So here we may get 2 loops, 3 loops or many loops, and each loop or each wavelength or frequency will give a distinct note. So based on what frequency you want, we can control the nodes here as well as the nodes and the loops. So this is one practical example of standing wave. Now here we'll try to find out an equation for a standing wave. To understand this, let us consider 2 waves of same amplitude, which means A is same for both the waves, frequency same frequency, which is seen in omega, and wavelength which is same, but the waves are traveling in opposite directions as seen by the signs here. One wave is of the form sine of kx minus omega t. So this wave travels along the positive x direction, and there is one wave of the form sine of kx plus omega t, and this wave travels along the negative x direction. So when these two superimpose, then what we get is, we'll rewrite it. So what we got is, we got y1 is equal to a sine of kx minus omega t. This is the equation for one wave. And other way we call the displacement as y2. Y2 is equal to a into sine of kx plus omega t. Now by the principle of superposition of waves, the net displacement at any point which you call as y, this net displacement is equal to the vector sum of individual displacements. Adding this, we get y is equal to y1 is a into sine of kx minus omega t plus a into sine of kx plus omega into t. Now we know that sine c plus sine d is equal to 2 times sine of c plus d by 2 into cos of c minus d by 2. Putting back here, we get y is equal to a, we can take it as common, so it becomes sine of, we can take even 2 outside, so 2a into a, because the form is 2 times, so that 2 is taken outside, so it becomes sine of c plus d by 2. So c here is, we can take this whole thing as c, this whole thing as d, so it becomes sine of c plus d by 2 into cos of c, which is kx minus omega t minus kx plus omega t by 2. And if we solve this further, y is equal to 2 into a into, it becomes sine of, from here this gets cancelled. Now what remains is, it is 2 times kx by 2, which becomes just k into x, because it becomes 2 kx by 2, that gets cancelled, into cos of, if we open the bracket here, it becomes kx minus omega t minus kx minus omega t. From here kx gets cancelled, and what we get would be minus of 2 omega t by 2, but cos of minus x is plus cos x, so this becomes just omega t only. So this is what we get for y. We can rewrite this as y is equal to, we can group this into a single term called as some capital A. So y is equal to capital A into cos omega t. So this is the equation of a standing wave. Now observe carefully here that in this case the amplitude of any particle is not constant. For each wave, if you had individual waves, they had same amplitude, which was a, and then a, which means every particle, if you had only one wave moving, then every particle in that wave will have same amplitude. But here the amplitude itself is a function of distance, because a is equal to 2a into sine of kx. Now keep in mind that this represents an simple harmonic form. That means each particle here would undergo oscillations. So even here also the particles would vibrate, they oscillate, but each particle will have different amplitude, but the resultant wave, which is standing wave, will have the same frequency and same wavelength as the individual wave. So the wavelength will not change, the frequency will not change, but the amplitude of each particle will vary. So, as seen earlier, we'll find out as to at which point we get nodes and antinodes. To understand this, let us recall the expression for standing wave with only its amplitude. So amplitude is given as 2 into A into sine kx. It depends at the distance also. So the resultant amplitude, which is called as capital A, is given 2 into A into sine kx. As seen here, it is the function of distance. Now here, if we take sine of kx, or rather if we take 2 into A sine of kx, its mod as 0, it implies that sine kx is equal to 0. So trying to find out at which point is the resultant amplitude equal to 0, because it's a function of distance. Now from here, since sine kx is 0, this implies that kx is equal to n into pi, where n is equal to 0, 1, 2, 3, etc. But k itself is given as 2 pi by lambda. So putting it back here, we get 2 pi by lambda into x is n into pi. From here, pi gets cancelled. Therefore, x is equal to n lambda by 2. But again, let us recall that n is equal to 0, 1, 2, 3, etc. When you put x is 0, when you put n is 0, we call it as x0, that is equal to 0, which means at the starting point itself it is a node. When you put n is equal to 1, we call it as x1, that will be lambda by 2. When we put n is equal to 2, we get x2, which will be 2 times lambda by 2. From here, if we look at, we can keep writing it. If we look at distance between any two nodes, for example, if we take difference between x1 minus x0, it's lambda by 2. So what is saying is, at the distances where x is equal to 0, that is when x is equal to 0, we get a node here. When x is equal to lambda by 2, we get a node here. So distance between this node and this node is lambda by 2. Again, when x is equal to, we'll call it x0, x1, x2, when it is 2 lambda by 2, that is 2 lambda by 2, which is same as lambda, that is from here to here, the distance is lambda. So at these points we get a node. So at the node, the particle will not oscillate, there will be at rest. This is something interesting, because in case of a simple harmonic motion or wave motion, each particle will oscillate, it will vibrate, and each particle has same amplitude, but here it is not. For example, here the particle here will have the highest amplitude, which in this case we'll see in a minute, while the particles on either side of it will have a lesser amplitudes, and the particles at the mean position or at the points here called as nodes will have 0 amplitude. We will find out the points where the amplitude is maximum, where the resultant amplitude was given as 2a into sine of kx. Suppose we take a point where this a is equal to 2a. That this implies that, this means that 2a into sine of kx, its mod is equal to a. That is, here the amplitude is maximum. Now here we can find those points. If we solve this, then this implies that sine of kx is plus or minus 1. This means that k into x is equal to 2n minus 1 pi by 2, where n is equal to 1, 2, 3, etc. Again, from here we can say 2 pi by lambda into x is equal to 2n minus 1 pi by 2. From here pi gets cancelled, therefore from this we can say that pi gets cancelled, x is equal to 2n minus 1 lambda by 4, where n is equal to 1, 2, 3, etc. Suppose if we put n as 1, let us call that x1. So it becomes 2 into 1 is 2, minus 1 is 1. So lambda by 4. Or we just write directly here. Next distance is putting n as 2. So it becomes 3 lambda by 4. Again, next putting n as 3 becomes 5 lambda by 4. It goes like this. Again here, if we look at the difference between any two points, that is the points where the amplitude is maximum, is called as antinodes. So if you look at the distance between any two antinodes, then it will be difference of these two, which is 3 lambda by 4 minus lambda by 4, that is 2 lambda by 4 is lambda by 2. So as seen earlier, even in case of nodes, the distance between two nodes was lambda by 2. Similarly, the distance between two antinodes also is lambda by 2. That is, the distance between this node and this node would be lambda by 2. The distance between this antinode and this antinode would be lambda by 2, which means distance between a node and antinode would be 1/4 of wavelength. Now as seen here, at the node, that is, so particles here, they'll have minimum or zero displacement, and the particle, when we increase from the mean position, they'll have a different amplitude. And the particles here at this point, these particles will have the highest amplitude.